Hello everyone, my name is Wang. Today I'm very honored to come here to share our recent work called Sci0, an open foundation model towards universal humanoid Loco-Manipulation. So without further ado, let's jump to the major content. So in the past few years, we have been seeing a carbon explosion of robotics. Nowadays, you can take a Waymo self-driving car in downtown San Francisco, Bay Area, Los Angeles, Phoenix, and these self-driving vehicles sometimes even drive better than human beings. And also with Unitree's G1 humanoid robot, you can play very fancy Kung Fu style motion. And if you see this year's Chinese Spring Festival Gala, you will be amazed at how robust and agile the current humanoid robots are nowadays. And also with robotic manipulators, for example, this is the one from a company startup called Journalist. So with these robotic manipulators, you can perform very fine-grained and highly precise manipulation tasks. And these are mostly driven by the recent vision language action models. So with so many successful examples, what are the driving factors behind the scenes? So what drive this recent success in robotics? To me, there are three major factors. The first factor is, of course, hardware. So on the hardware side, in the past few years, the whole community has developed many good hardwares. For example, this Unitree G1 humanoid robot opens up a lot of capability for locomotion. And also this sharper wave dexterous scan also has very high dexterity and very high resolutional tactile sensing capability, which opens up a lot of which opens up a broad range of applications. And on the bottom left is Decoupling capture device, which is developed here by Shu and Song's group. And this Decoupling device basically accelerates data collection for robotic manipulation, for dexterous manipulation. And the other driving factor is the algorithm. So on the algorithm side, there are many exciting ongoing threads. So first one is vision language action models. So this is on the bottom right is Pi 0.5 architecture. So more or less the recent VLA models follow this common Pi practice. So you have this pre-trained VLM model from large-scale internet data, followed by an action expert that is trained on some in-domain robotic demonstrations. And these VLA models really enable kind of generalization in manipulation. And equally exciting is word models. So recently, video generation model-based word models can synthesize data or can synthesize the scenarios by inputting some action conditions into the model. So here is a model released by Google DeepMind robotics team. So this Gemini robotics model basically use a video generation as a simulation platform to test the policy. So you don't have to go into the real world to evaluate your policy. Instead, you can just use a word model to rule out your policy for faster evaluation. And to really learn these powerful models, we definitely need data. So on the data side, we now have very good tools to collect large-scale data. So on the bottom, on the top left, it's NVIDIA ISACSIM simulation platform. So with ISACSIM or Google's Majoko simulators, you can now synthesize, you can now run large-scale simulation in parallel for locomotion. But of course, for manipulation, there's still a huge sim-to-real domain gap. And to address that issue, people develop data capturing devices or pipelines to collect the data from the real world. So on the top right is a Jello system developed by Berkeley Peter Bell's group. So in this Jello system, you have two leading devices that this human operator is controlling. And these leading devices control the robot arms to perform a manipulation task. And then you can capture the observation from a third view camera and as well as the robot states from the robot themselves. And by leveraging this human teleoperated data, you can train some imitation learning policy and directly learn from human preference. So even with these very powerful driving factors, nowadays we are still very far from having real humanoid robots to go into the industry to perform the real work. For example, the ideal case is that we want the humanoids to go into each manufacturer to, for example, assemble a car, or we hope that humanoids can go into each home to perform those daily household tasks. We are still very far from having those humanoid robots to perform the real work. So why is that? So this is because for locomotion, they are more or less solved by large-scale simulation. However, to have humanoid robots to perform the work, we also need manipulation, and we also need intelligence. So at the end of the day, we want the humanoids that can follow the human instructions to reason what need to be done, and then perform the work with some mobility, with some manipulation capabilities. So it's from today's perspective, it's still quite hard to combine locomotion with manipulation, and it's even harder to incorporate intelligence into those local manipulation pipelines. So to address that issue, the mission of my lab is to build an intelligence model to solve humanoid local manipulation. So what we want to do is we want to develop some intelligence model, such as large-scale VLA models, to really control the robot in a unified fashion. We want the model directly output the joint states to control the robot in a unified fashion. We don't want the locomotion separate from the manipulation capabilities. Of course, to address this issue, we need to first dissect this problem into different parts. So first, we need to understand what kind of data we need to use to address this issue. So if you work on robot learning, you probably already seen this data pyramid. So usually we work on this data pyramid to learn some policies from the real world data, from data. So on the very bottom, it's internet data. So you can easily download a lot of videos from the internet. They contain certain level of manipulation information inside. However, there are still a lot of noises inside those internet data. And for example, there is always viewpoint discrepancy. So the viewpoints are very different from the robot viewpoints, which creates a lot of domain gap. And also, this internet videos or internet data doesn't really contain action information that much. So if we go one level above, we will use probably simulation data. So this is a RobotVerse project that I got involved in. And with the simulation, again, you can solve locomotion very easily by running large-scale simulation. However, there is always a huge domain gap between simulation and the real world. So there is always a physics gap. So it's hard for some manipulation skills that require, for example, some highly precise physical understanding of the visual world. And also, there's always a visual fidelity. The visual fidelity is not always guaranteed with current simulators. And on the very top is real-world data, which is captured from teleoperation. And the real-world data, as we discussed in previous slides, is of very high quality, and you can easily learn some imitation learning policy by using this real-world teleoperation collected data. But of course, the collection cost is always considerable because you need to deploy the robots into the real scenario. You need to have a human teleoperator to control the robot and to capture the data. So it always comes with a certain collection cost. And on the model side, there are also some questions that needed to be answered. So right now, as I mentioned in previous slides, if we work on vision language action models, we more or less follow the pi practice. We usually work on this fixed-based bimanual manipulation task, and usually the action space we are dealing with are like around 18 degrees freedoms. And this is because we usually have 2 arms. Each arm has 6 to 8 degrees freedoms, plus some mobility of the robot base. So in total, we usually work on 18 degrees freedoms following the pair practice. And there's no locomotion involved. However, if we work on humanoids, so we are dealing with more degrees freedoms. We are dealing with more flexible robots. For example, this Unitree G1 robot on the arm, it has 7 DOFs, and on the waist it has 3 DOFs, and hand also has 7 DOFs, and the leg, one leg has 6 DOFs. And we are trying to solve a Loco-Manipulation task, and the total action space we are dealing with has about 43 DOFs for this Unitree G1 robot. So in that case, the current VLA models cannot really deploy it into this humanoid robot off the shelf. And also on the learning side, we usually follow a 2-stage training. In the first stage is a pre-training stage. We use a multi-model internet data to pre-train a VLM backbone, and followed by a post-training stage, which leverage some in-domain teleoperation data to align the action space. And the action head we usually use is a continuous action head that is trained with some flow matching laws. However, there are some other unsolved questions. For example, can we explore some alternative stage training? And can we explore other data sources for pre-training, etc.? And do we need to do tokenization of the actions? So all of those are some outstanding questions that needed to be answered for humanoid local manipulation. And also equally important is deployment. As we all know, we try to deploy some algorithm into the real robot in real time. And here is an example that we simply deploy a VLA into a Unitree G1 robot. As you can see from this video, there's always pause between actions and also action jittering. So that means the real-time capability is still a problem, and also because of the inference gap, inference delay of the VLA models. So this creates some training and test time gap, which will make the deployment harder. And also we try to support diverse real-world tasks when we deploy the VLA model into the real world. So to answer these questions, we look at them. We look at different aspects of the question. So on the data side, in contrast to existing methods that more or less leverage internet data, we opt to use egocentric human data. So this is because. So here I want to first show an example of this human egocentric data. So this data is captured by Apple Vision Pro. So what you see is is a person that is doing a bimanual manipulation task, and we capture this egocentric video, and also at the same time we track the human hand as some action representation. And we try to use this egocentric human data because of several reasons. First is scalability. Second is alignment in the observation and the action space. Let's dive into each part in details. So in terms of the scalability, in addition to the Vision Pro that people cannot wear it too long, we actually develop our own capturing device. So this is a pretty simple 4-camera headset. So we put basically 2 stereo cameras on a cap, and then we connect it to some like a Raspberry Pi to capture the data from an egocentric view. And as a result, with this very simple setup, we can capture 5 hours of data each day by each person. So this is pretty scalable in the sense that you don't need to affect the human daily work. So as long as a person is performing their task, and we put on this cap, we can capture their daily manipulation work. And right now we have already collected over 1,000 hours of data using roughly 20 devices. And moving forward, we are this year we are targeting 10,000 hours of data. And of course, in the future, we will keep increase the scalability of the data. But of course, this is already beyond the scale of a lab. So we may need collaboration with through crowdsourcing or with some data vendors. And of course, if you are interested in this, I will definitely appreciate any type of collaboration to really scale this egocentric data collection. And the other reason why we want to use this egocentric human data is that we have good observation alignment. So if you look at the captured images, you realize that they are more or less from the same viewpoint with the humanoid robot. So there is a natural alignment in the observation space so that we don't have a lot of observation gap. And similarly, if you use a human hand tracking as a representation for this human data, we also have a natural action space alignment, or more or less we use a shared n-factor control. And this is because this human hand has a similar morphology to the humanoid hand, and we use a similar key points or joints representation to represent both the human hand and the humanoid dexterous hands. Go ahead.
So for the previous slide, the camera can only see the hand and forearm, right?
Yeah.
What about the other like legs? Are they?
Right.
Yeah.
So I'm going to talk about some details during the pre-training stage of the VLM. But the short answer is that when we pre-train the VLM, we will only use hand tracking as a objective. However, we can also solve IK to get the whole body motion. So in this case, because this Vision Pro has a very limited field of view, you don't see a lot of your whole body, right? But in our capturing device, we have two front-facing cameras. We have two down-facing cameras. The down-facing cameras can see pretty much like the whole body, so that you can use that to estimate the whole body motion. So in fact, we use SAM3D to estimate the whole body motion. Yeah.
And another question is, the robot is 3-finger, right?
Yeah, it's 3-finger.
Fingers for human hand.
Yeah, for again, so in this case, the data is used for pre-training, but of course we do use a 5-finger glove to do teleoperation of that 3-finger hand. What we do is we only use these 3 fingers to control the 3 fingers on the humanoid robot. But we also changed that 3-finger hand with we replaced that with recent Wuji 5-finger hand. Yeah. Thanks for the question. So coming to the teleoperation data, because we still need the teleoperation data to align the model to a certain robot. So we need to capture highly precise teleoperation data from the robot. So this is our capturing setup. So we have this Pico 4U VR headset along with some wrist motion tracker and the full motion tracker. So there are some IMU and RR-based motion trackers. So with this, together with the VR headset, you can track the whole body motion, including the head, the torso, and the leg, etc. And at the same time, we use this Magnus glove to track the precise hand motion, so that you have the whole body motion, including the hands. And we use this setup to teleoperate the robot, like the whole body of the robot. And here is some details of the teleoperation system. So we basically, for the hand, we directly capture the motion of the fingers, and we map them to the humanoid space to control the humanoid hand. And for the upper body, we have the motion from the wrist tracker. We have the wrist position, and also we have the head position. So we solve a multi-target IK problem to get the whole body motion, the upper body motion, and we use that to control the arms of the robots. And also we get the torso motion. And together with velocity and the Fourier, we control the lower body with a low-level reinforcement learned policy. So basically, to summarize, for the upper body, we use a multi-target IK to get a full upper body motion to control the robot. And for the lower body, we use AMO-style reinforcement learning policy to control the mobility of the robot. And now I want to diverge a little bit to talk about another paper we recently got accepted to ENGR 2026. It's called Humanoid Everyday. So this paper is a Dataset paper. So this paper features a high-frequency humanoid dataset spanning diverse everyday tasks. So we use a previous setup to capture the data. So this dataset, again, features a diverse collection of humanoid tasks. So we cover over 10,000 trajectories, 3 million frames, and 260 tasks using Unitree G1 and H1. And the right figure is a task distribution. As you see, this dataset has a pretty diverse coverage of daily tasks. And also we include some bipedal loco-manipulation, the human-robot interaction that are super rare in other datasets. And of course, to enable this efficient data collection, we develop a dedicated pipeline. And in this pipeline, we offload I/O to make sure the control loop is fast enough and responsible enough. And as a result, we see great improved performance for teleoperation. So we reduce the control delay from 500 milliseconds to 20 milliseconds. So this basically half the data collection or teleoperation time. And therefore, we capture 30 Hertz multimodality streams. So that includes RGB, depths, and the LiDAR, basically perception signals, and also proprioceptive signals such as the joint states, tactile odometry, and the IMU from the robots. And also we have the human actions and the task descriptions along with other sensory signals. And also we develop a customized data viewer to help you debug the data collection procedure. So we have text description and the serve view video streams and also egocentric video streams, as well as the point cloud and depth visualization, so that you can easily debug your collected data with this data viewer. And the other very interesting thing we do in this paper is comparison of existing policy learning method using this loco-manipulation data we collected. So we basically train and fine-tune several imitation learning policies and the VLA models on different loco-manipulation tasks we collected in the dataset. So in total, we benchmark from diffusion policy to 3D diffusion policy, all the way to recent VLA models such as PI 0.5 and GRUT 1.5. And we have some interesting findings. So the first one is very straightforward. VLA models consistently outperform existing imitation learning policies such as DP or DP3, and this again confirmed that large-scale pre-training is really useful, and we really need to scale up the data to pre-train the model. And the second, the NVIDIA GRUT N1.5 achieves best overall performance. And the last bitter lesson is that our policies perform still quite poorly on highly difficulty manipulation tasks, such as the last one. And as you see, all the existing methods pretty much failed all of the tasks. So that means there's still huge room for improvement. There are more research needed to be done in this field. And then finally, we develop an evaluation toolkit for people to evaluate their policies that are trained on this humanoid everyday dataset, because we believe not everyone that is interested in humanoid learning has a real robot to evaluate their policy on, to compare, that has ways to compare their methods to existing ones. So we developed this cloud evaluation platform so that people can send their policies to us, and we evaluate the policies in the real world for them. So basically what we do is we stream the real robot data and record the success rate, and we send them back to the users. So users can either upload their policies to our server and we run inference locally, or they can directly send a control command to us and we run some remote remote policy rollout and evaluate the policies using our real robot. Yeah, so this is pretty much the humanoid everyday work. And now let's go back to the original study. So going back to the original size 0 model. And on the model side, again, so more or less existing VLA models follow this common practice. They have this pre-training stage on large-scale internet data, followed by some post-training, some in-domain collected data using some bimanual manipulation tasks. So different from this existing VLA models, what we do is we try to build a multi-stage training that relies on human egocentric videos. So this is an overview of our pipeline. So what we do is we pre-train, instead of using internet data, we use this human egocentric videos for pre-training. So we pre-train a VLM using this egocentric videos, followed by a post-training of action expert using in-domain collected teleoperation data. And finally, we deploy the learned model into a real robot for whole body Loco-Manipulation. So let's dive into the details of the model or the training. So in the model, in the pre-training stage, again, we are using the human egocentric video for pre-training. So we basically feed the human egocentric videos along with video descriptions into the model. And we ask the model to predict some discrete action tokens. So those discrete action tokens are basically represent the human hand motion. And this is basically the training objective. And in fact, we use 829 hours of EgoDex dataset for pre-training. And this dataset is basically captures a lot of egocentric video using Apple Vision Pro. Yeah, go ahead.
Well, you guys only use ego data for this one.
Yeah.
Have you guys do some experiments using DAX-Rumi?
We haven't, because there's no large-scale DAX-Rumi dataset available as of now. Yeah, we try to use DAX. Sorry?
It could only be better.
Yeah. But again, DAX-Rumi is not. DAX-Rumi is great, but the capturing speed is not as fast as this like a headset, because it doesn't affect human productivity. Yeah. And in terms of the action representation, we use this 9 DOF racer pose plus 3 DOF position per fingertip times 5 fingers. So if you do the calculation, there's 24 DOFs for each hand, and then in total we have 48 dimensional action vector to represent the action. So this is a prediction target. And we do one-step prediction, because in practice we found that even one single step prediction, action prediction can already give the model a very good understanding of the task and the manipulation, etc. So to save computation, we don't do like a long horizon prediction in the pre-training stage. And of course, again, in that action representation, we use a discrete token representation. So that means we need a tokenizer to compress continuous action representations into some discrete tokens. So what we do is we use a faster tokenizer that is developed by physical intelligence. So in a nutshell, this faster tokenizer converts some continuous action representations into the frequency domain using discrete cosine transform, followed by some quantization and a byte pair encoding, so that you convert some continuous action representation into some discrete action representation. So in fact, we fine-tuned the faster tokenizer using 500 1,000 randomly sampled pairs, sampled actions from the Egocentric dataset, so that we can compress this 48-dimensional action representation into a 13-dimensional action tokens. And here is a comparison between the original fast tokenizer and our fine-tuned version. So as you see, we achieve a lot of reconstruction loss deduction at the cost of a longer token length. But still, we get better reconstruction loss. We use this for our pre-training stage. We use the fine-tuned version for our pre-training stage.
Why is the token length longer after? Because I saw the dimensionality decreased from 48.
Right. So this is off-the-shelf fast tokenizer. They are trained on, for example, some bimanual manipulation tasks. So naturally, they have very short token lengths, very small token lengths. Well, after fine-tuning, because we are basically adapting this fast tokenizer to the Egocentric case, which has a longer token length. But still, comparing this 13-dimensional vector is much smaller than the 48 original token actions. Yeah, so this help speed up the training and also make the convergence much faster of the pre-training stage. And then in terms of post-training, we basically freeze the pre-trained VLM backbone. So this VLM backbone is taken from the first stage. We freeze it in the second stage, and we only condition the VLM features in the action expert. So in this stage, we basically train this action expert using some in-domain collected teleoperation data. And we use 30 hours of a humanoid everyday dataset I discussed in previous slides for this action expert training. And the objective is flow matching on continuous action. And one very important innovation we did in this action expert training is MMDIT head or multi-model DIT head. So here is a comparison between the MMDIT head in the VLA model to the naive DIT head in most VLA models. So all of the existing VLA models more or less using similar design for the action prediction. So in this naive DIT head, you have this VLM features that are mixed with these action features at a very late stage of this DIT module. And so the feature mixing between the VL features and the action features happens at the very end of the model. So, however, in this MMDIT head we use, so we basically concat the VL features with the action features at the very beginning, and then we convert the cross attention into a joint attention, which is essentially a self-attention. So this helps the feature mixing of the VL feature and the action feature. And it turns out this MMDIT head already gives a huge performance boost compared to the naive DIT head. So I would recommend everybody who's working on VLA, try this MMDIT head. So this MMDIT head is a very common practice in video generation, but not many people are using it in VLA models. If you work on VLA, definitely use this one.
So if you're already doing self-attention model, why are we still concatenating the vision language action before sending them to the
If you look at the DIT head, the self-attention only happens on the action tokens.
But for that one, doing self-attention for both the VL training and the right?
They first concat the features from VL tokens and the action tokens, and then they do the joint attention.
Yes. But I guess my question is, if you assume that the concatenation and self-attention are both transfused information from VLM,
right?
But they seem that like why do we do both of concatenation and self-attention?
Because on the one level, Let me think how to answer this question. You still need attention across different tokens, and at the same time, you want the action features mixing with the VL features. What they do is they are basically doing some sort of channel-wise attention, along with the spatial attention. Yeah. I don't know if I answered this question.
That makes sense. Thank you.
And finally, in terms of a deployment, so again, we want to deploy a whole body controller into the real robot. We control both the upper body, the arms and the hands, as well as a lower body. Basically, we want the model to perform manipulation while they are moving. And to do that, again, for the arms and the hands, we do joint-based control. And for the lower body, we do a AMO style policy. So we do basically a reinforcement learning style policy to control the lower body. And the VLA model outperforms the commands for arms and hands and for the lower body at the same time. And the other very important issue is efficiency. So we definitely want the robot to be controlled in real time. We don't want any pause during deployment. We don't want any action jittering. So to do that, we have a real-time trunking system implemented. So here is a video, as I showed in previous slide. So this is one without real-time capability. So as you see, there's always action pause. And also there's some jittering between actions. And this is because, let's use the example from the paper called Real-Time Execution of Action Trunking Flow Pauses as an example. So this is because we are basically using, when we do inference with VLAs, we are predicting a long horizon. We predict a sequence of actions. So let's suppose we predict from A0 to A10 in the first action trunk. And here we try to avoid obstacle. And then we try to predict a second sequence of actions. But the prediction only starts at between A3 and A4. And the second sequence of action can only be ready at time equals at t equals 10 because the VLA model requires a certain time of inference, right? So there's always a long inference delay. So at the time when the second trajectory, when the second sequence of actions is ready, the model or the robot has already executed from A4 to A10. So if you directly switch from A10 to A11 prime, so there's a huge action jump. So you will see a lot of action jittering. A naive solution is to ensemble these two trajectories. However, if you simply assemble these two trajectories, so you will hit the obstacle. So this is the issue with temporal ensembling. And how can we solve this problem? So it turns out the problem is because of some overlap between two action sequences. So again, let's use this as an example. So we assume the first action trunk starts from t minus s to t minus s plus h. So that's the first action trunk. Well, the second action trunk, which is currently predicted by the model, starts from t to t plus h. So there's always overlap region, right? So in the overlap region, the robot is executing the tokens that is predicted in the previous trunk. And when we're predicting the second trunk, we don't know that information. We don't know the robot is executing the second part of the action sequence. So to address this issue, in this paper called Training Time Action Conditioning for Efficient Real-Time Trunking, they come up with a solution called training time imprinting. So basically, they treat this problem as an imprinting problem. So the idea is pretty straightforward. So if we know the second part of the action from the previous trunk, and if we can condition on it when we predict the second trunk, then we can more or less guide the prediction of the second trunk. So this is basically the idea. So during training time, we assume we know some of the first few tokens, and we condition on the we condition on them, and we only predict the second part of the action trunk, so that we basically guide the prediction of the second trunk with some known tokens, with known actions, and we synthesize some inference delay during training time, so that we can use that to implement the missing part during inference time. So this is basically what they call the training time real-time action trunking. And we implement this for humanoid robotic control, and we deploy that into our system. And of course, this requires some low-level communication, and we implement low-level communication logic. Here we have two parts. One is the client, which is a robot itself, and the second is the server, which is a GPU desktop that runs some VLA inference. So on the client side, it captures the observations and sends the observation to the server at 30 Hertz. And when the server receives the observation, it passes it through the real-time trunking and the inference module. And in this module, it has two parts. The first part is a control loop, which is always to consume the latest action and send it back to the client side for execution. The other one is the inference loop, which is real-time trunking we discussed in previous slides. So in this inference loop, we always try to predict the latest action based on some knowledge of the actions that is being executed on the robot side. So by doing so, we try to avoid any discontinuity of actions. And this inference loop is trying to basically predict the latest action trunk. So as a result, we can achieve real-time control. So here is the original system without real-time control. As you see, there's always a pause between actions. And on the left, it's the system with real-time control capability. So as you see, the motion, the action is very smooth and is very continuous. Yeah, to further visualize predict action, we pick up one particular joint angle, and here the visualization, the curve in green is the next predicted action without real-time trunking, while the one in purple is the next action with real-time trunking. As you see, the one with real-time trunking pretty much follows the trajectory of the previous action, which guarantees the continuity, while the one without real-time trunking has a sharp jump from the previous action. So that's a further show that the real-time trunking helps make sure the predicted actions are continuous and smooth. And that is basically the overview of the system. And also we compare our system to other state-of-the-art methods for humanoid robotic control. We compare our method to NVIDIA's GR319 1.6 and also Pi 0.5. And we show on the right, under different tasks, different types of tasks, our model consistently outperforms all of existing models. And also on the left, we have each subtask success rate, and we show that our model, again, achieves a lot of performance improvement over baselines. And basically, to summarize, our model is 40% better than NVIDIA GR319 1.6, which was a state-of-the-art model, while we only use 10% of the training data compared to GR319 1.6. So if I remember correctly, GR319 used over 10,000 hours of pre-training data, while our method only used around 800 pre-training data. And also we have a detailed ablation study to benchmark each submodule of the whole system, and we compare and a very challenging long horizon task. So this task involves right arm pick and place, left arm pick and place, and do arm holding, and the task is considered is only considered a success when all of the subtasks are successful. And as you see, we benchmark different modules, and adding the EgoDex pre-training really helped the model. And also we compare whether MMDIT had helped the performance improvement, etc. So yeah, this is pretty much the result. And finally, we have a visualization video demonstration from the USC campus. So let's see the video, although it's a little bit long. So we're doing whole body, like a local manipulation for some daily household tasks. So this is all controlled by the VLA model. So this is a policy route. So this is not teleoperation. We also have some each subtask we evaluate on for quantitative comparison, as I show in previous slides. And again, all of these are evaluated on in real time. We don't do any speed up the video. So we have 8 tasks in total that involves basically whole body like a local manipulation. Yeah, so this is pretty much the side zero work, the humanoid body VLA work, and yeah, go ahead.
Yeah, it's really amazing downloadable, by the way. Great locomotion.
Yeah, thanks.
I have a quick question.
Yeah.
So what if the experiment is changed into those hard long horizon solving manipulation tasks? Does that mean side zeros gonna perform the polling even more than all the leading ones?
Like a pi 0.5?
Or yeah.
I think if we do tabletop manipulation, definitely pi works better because they are more they train on more of those data, And for this, for the task we considered like a local manipulation, I don't think pi 0.5 or 0.6 works better because there's always a domain gap in the pre-training stage. But for post-training, we use the same data for training all of the methods to make sure they are evaluating in a fair fashion. Yeah. Now that we only have a little bit of time, I also want to share a little bit our another ISS submission called HumDex. So this paper is a small paper but an interesting one. So this is basically a portable IMU motion tracker-based whole body teleoperation system. So in a very high level, we are doing whole body teleoperation, including both the upper body, the lower body, and also the hands. So in this case, we change the we replace the 3-finger hands with the 5-finger Uji hands for challenging dexterous manipulation tasks. And also we change from the VR-based teleoperation system to an IMU-based whole body motion tracker system. So how do we do that? So for the whole body, excluding hand, we use existing humanoid controller, such as the Twister 2 for teleoperation. And for the 5-finger hands, we use learning-based method to do this teleoperation. So this is because we only have 5 IMU trackers on the fingertip, but we need to control a 20-DOF dexterous hand. So we need basically either optimization-based IK solver to get the full hand motion, or in our case, we use a learning-based method to do the retargeting or to do the mapping. So how do we do that? How do we learn this mapping network? So we have a very straightforward pipeline. So basically, we use a learning-based data-driven approach. So we collect over 20,000 frames within 20 minutes using optimization-based hand teleoperation pipeline. So basically, we use this IK solver to get the full hand motion from 5 fingertips and to basically collect data from the real world. And this gives us some real world data, real world human teleoperation data. However, of course, as you can imagine, there are some failure examples in the data. So we ran an automated filtering step to remove all the abnormal angles and some field pinch to only keep the correct data or to only keep the good data. And then finally, we do a simple supervised training of a small MLP to learn the mapping from the hand space to the dexterous hand space so that we can do teleoperation. So this is basically the overview of the work. So as a result, we can achieve some challenging teleoperation tasks. So this is a human operator that wear this full body IMU trackers and use that to teleoperate a robot with 5-finger hands. So here's another example. And we have more examples, more challenging examples. This is opening a door. And here's a grasping example. And here's another pick and place task.
Can I ask a question?
Yeah, please.
How long does it take for somebody to be as good as this teleoperator in the video?
I think this human teleoperator probably takes 1 hour for adapting to the system. About 1 hour. Yeah, it's not that hard. And here, with the collected data, we can learn some policies and rule out the policies in the real world. And here is a policy evaluation in the real world. Yeah, also we compare this IMU-based motion tracking system to a vision VR-based motion tracking system. We show that compared to the vision-based system, this IMU-based teleoperation system has a bit better in terms of collection time and the collection success rate, and also final policy route success rate. And also we benchmark this learning-based hand teleoperation to some optimization-based teleoperation. So here is a visualization. As you see in the middle, here are some failure cases of the optimization-based teleoperation. So there are always some posts like this OK post, or some posts that the optimization-based methods always fail, while this learning-based method like it doesn't fail this special posts or special motion. And also on the right, we benchmark the learning-based method consistently outperform this optimization-based method under like different challenging tasks. And finally, in this work, we also explore learning with human data. This is because with this IMU-based tracking system, we can directly collect data with a human without teleoperating a humanoid robot. So this is because for the same task, as you see from this video, human performing a task much faster than teleoperating a robot to perform the task. So if we can leverage this human data to augment teleoperation, so we can like speed up the learning with more data. And how can we do that? We basically put on egocentric RGB camera in the similar viewpoint to the humanoid robot, so that we align the observation space in a similar configuration with the previous size 0 work. And at the same time, we try to synthesize or approximate the proprioceptive states with some retargeted states of the hands, so that we use a similar state representation. And after that, we train ACT policy with a mixture of human data and the humanoid teleoperation data. And we can show that under some unseen scenarios, we can capture some data with humans without doing any humanoid teleoperation, and we augment the model training with this human data, and then we test it under these challenging scenarios, how the learn policy works in the real world. And as you see from the right figure, by leveraging more human data, the model consistently outperforms the model learned with pure robot humanoid teleoperation data. So this is that was pretty much the HumDex work. So finally, I want to briefly discuss some future directions we are currently focusing on. So on the data side, I use this figure as a quick example. And on the data side, we are trying to scale up the data from 1,000 hours that we are currently working on to 1 million hours. Of course, this is quite challenging and beyond the lab scale. This requires collaboration with different research groups, with, for example, some data vendors and the industry people. And I'll appreciate, as I mentioned in previous slide, any type of collaboration if you're interested in scaling up the human egocentric data as well as humanoid teleoperation data. And to do that, we need a better capturing device, such as Decoupling or other better capturing device to really scale up the data collection. And finally, we need larger models and more data efficient models to consume the large data to incorporate the intelligence into the foundation models for robotics. So that is probably all the topics I want to discuss today. With that, I want to thank all my great students. Without them, all those works cannot be possible. And I also want to acknowledge funding agencies for supporting our work. And finally, I want to thank all of you for coming. And I'll stop here. I don't know if we have time for questions, but I'm happy to answer if we have time. Go ahead.
On the human intelligence or to the physical intelligence, what about behavioral priors and understanding the context and the environment in which the robot is in? Do their behaviors change, or are they essentially supposed to just follow the task as is? Is that a future direction?
Sorry, can you repeat the questions?
Yeah, essentially
So I
to
don't.
understand whether the task alignment and the context in which they're performing that task, to what extent does that affect the way in which they actually perform the task? Essentially to understand the human behavior, does the context, environment affect?
Oh, I see. You are seeing whether the model is learning some human behaviors, and can we leverage those human behaviors to adapt those humanoid robots?
Yeah, and they would not respond exactly as tasked, but based on the environment. Yeah.
I see. I think with those human egocentric data, so we first learn human behaviors, as you mentioned, because we have very rich behavior level information. At the same time, you see more environmental information like the objects, the contact, and the background, etc. I think I don't have a clear answer whether the model is learning, let's say, 40% of behavior, 60% of environment, but I guess they are learning both. But I don't know the percentage of or which part is more learned from the model.
I guess I'm curious about the quality of your egocentric data. Like, I think there are a lot of data sets even on the internet of monocular egocentric data.
Like a build AI.
Yeah. So do you think stereo is critical to get a high quality?
I think stereo is not critical in the sense that we, in the pre-training stage, we probably don't need the real physical skill. As long as we have some consistent 3D representation of the hands, then we can learn some behavior level information and the environmental information. But we need the consistent 3D estimation, right? So if the skill changes over time, then that creates some basically difficulty for the model to learn. So in that case, I think molecular videos can already be a good source of pre-training. But in terms of the build AI model or dataset, I don't think they come with some hand tracking. And doing hand tracking with egocentric camera is already a hard problem. Even though there are some good open source models such as Hammer or Dynamic Hammer, but if you try them on the in the open environments, there are always occlusion and loose tracking, etc. Yeah.
Thank you for the talk. You showed some impressive demos of the Psi model, the humanoid tasks. I'm just wondering, how many training examples of that task were in the model, or are those done sort of zero shot?
Yeah, so here in that, specifically in that demonstration, we don't do a lot of zero shot evaluation. So there's still, we deploy the model into the same environment where the data is captured. But for example, the object locations, the type might be zero shot, but the environment itself and the task itself is not zero shot.
Yeah, I'm thinking like, what do you think about like incorporating the force or torque into the model, like force aware or torque aware?
Yeah.
Would that be very helpful?
Yeah, that would be very useful because right now when we perform some fine-grained tasks and for example, grasping a grip, such as those examples, that requires some force-based control. But right now, this position-based control has a very hard time to perform those fine-grained tasks. So I think the force-based control and incorporating those force signals is very important.